get her on stage. Sabrina Speich, do I pronounce it right? Oh, fantastic. Oh, that's good. She's member of the Laboratoire de Météorologie Dynamique of the Institut Pierre-Simon Laplace.
Yes.
What does that institute do?
It is the Climate Institute where also Jean Jouzel is in the Paris area. It's federating all the labs working on the climate system.
And you're going to tell something, well, it's behind me. The role of the ocean in the climate system, an open question on Atlantic Meridional over the AMOC. I'll give you the stage. Sabrina.
Okay, so I will review briefly, and to change the slide is this one?
Yes.
Okay, thanks. So I will summarize briefly what is climate change and what we know generally. So the climate system is the whole Earth. So we are used to think about the climate as the atmosphere, but actually it is more complex. We have the ice, cryosphere, we have the land, the biosphere, what is living, and the ocean. 2/3 of our planet is covered by the ocean. And when you see the picture from the space, you don't see the atmosphere, you see just the clouds. And this is what see mostly the sunlight that warms our climate is the atmosphere is essentially transparent, or the sunlight is reflected by the clouds. This is why you see the clouds. So most of the sunlight that is not reflected back to space reach the surface and reach the ocean. And the ocean is made of water, and water has a huge heat capacity. You need a lot of energy to change the water temperature of 1 degree, because and this energy is therefore absorbed by the ocean, and it stays there for a long time. And also the water is a very fantastic dissolving medium, so it dissolves gases like oxygen, but also CO2s. And these oxygen and CO2s that do not stay at the surface, but follow the currents and go at depth. So it is really a fantastic medium. It is a fluid like the atmosphere, but much denser, and it is opaque. You cannot see through the lights. This means that the sunlight is essentially absorbed in the very few meters of the ocean. And so this is important for our climate change, our climate and also climate change. So climate is essentially a question of energy. How much of the energy that comes from the sun stays into the system? And what stays in the system and is changing today is the heating of the Earth. That is infrared radiation, so sunlight that is invisible is changing to infrared. You don't see it, but it is a physical law. So the Earth is there since billions of years, so it has been heated by the sunlight. Now it was in equilibrium, statistical equilibrium, so it rejects infrared radiation. But infrared radiation is not anymore transparent in the atmosphere. It is captured by the greenhouse gases. So today we have more greenhouse gases in the atmosphere, so we have more energy that is absorbed by these greenhouse gases, and it is brought down back to the Earth. So there is more energy in the system. The question is not just change in temperature, but change in energy. And so you are used to see the temperature increase, and this is a measure at the surface of the planet. And if we can separate what is the change in temperature over land and over the ocean, so the land is red, the ocean is blue, the blue is getting slower up. So this is the anomaly in temperature, and you see that the temperature in the ocean is increasing slower at the surface. But is this a measure of the total energy change due to climate change? No. Actually, we need to measure how the temperature change everywhere in the volume of the atmosphere and of the ocean and on the Earth. And so this is the evaluation that actually Karina was the first authors of how the energy is changing in our system. So you see the units is zeta joule, so 10 to the 21 joule, that is the unit for the energy. And here you see from observation how were the changes. So you can see that the changes are mostly blue. Blue is the ocean. Lighter blue is the upper ocean, and you go darker, it is the deeper ocean. So we had a lot of uncertainties because we didn't have many observations, and now we have more observations, so less uncertainties. But you need to compare this blue with the rest. So this is the Earth, continents, this is cryosphere, the ice, and this is the atmosphere. 90% of the surplus heat due to the greenhouse gases go into the ocean, only 1% in the atmosphere. So this is meaning that global warming is essentially ocean warming. And you can compare this number, so we are about 400 zeta-joule acquired by the system, compared to what was the energy estimate still living on Earth, estimated in 2010, so 15 zeta-joule compared to 400 zeta-joule acquired by the ocean. So the ocean is changing, and instead of having the stripes for the surface temperature, as Olga has, these are the stripes for the heat content, so the energy content in terms of energy for the ocean, and these are just trends from our colleague, first author Ling-Jin Cheng, that have been computed in terms of how much the temperature changed in the ocean in the first 2,000 meters, where we have a lot of observation for the moment. So you can see that it is changing, is getting deeper. So the ocean state is changing, and this has impact on both the chemistry and ecosystem of the ocean. And the impact of this warming is, of course, also felt in the sea level, and I think you will have a talk on sea level. So this is the sea level measured since we have satellite. So it is accelerating. We had 2.13 millimeter per year, and now we are more close to 5 millimeter per year. And this is the sea level trends. So where this sea level change. So it is not homogeneous. This is due to the ocean circulation. So you have structures where the ocean is warmer or the circulation stays there for a long time. This is the wind circulations here and there, likewise in the Atlantic. And then you have the tropical system where the currents move heat toward the Western Pacific and Indian Ocean here. But an important part of this sea level change is due to the ocean warming. So ocean warming comes also with extremes, and some extremes are the marine heat waves extremes. And these extremes are long-standing and very quick increase of temperature. The Western Mediterranean is nowadays already in such marine heat waves. And this is due both to the ocean warming and to the fact that the ocean is interacting with the atmosphere. And the atmospheric circulation is also changing. And we have a different forcing, clear sky, less wind, and this implies more warming of the upper ocean. That has an impact on the ecosystem. And if I wanted to show observation in the hurricanes, but I don't know if it works. So now, to improve this air-sea interaction knowledge, scientists try to develop observation, not only for planes, this is a NOAA planes, but also in the ocean with sail drones. So this is air-sea interaction, so you can see there. And also sub-ocean gliders and Argo floats that are means that measure the upper ocean heat content because there is a lot of heat release. And if I can say 2 minutes for the AMOC. So the AMOC is the global ocean circulation that we cannot measure except, I mean, we cannot measure the water parcel that do all this global tour because it takes hundreds of years, but we have observation to measure the intensity of this current and how it works. So in the polar regions, Arctic and Antarctic, there, it is very cold. The Earth's interaction makes the water really denser, so it's like a stone go down, and I think I have a kind of animation, maybe, no, it is not coming out. Well, and the water sink and start a journey, for example, in the North Atlantic, goes down to the Austral Ocean and do some loops before coming up and going in the other ocean basin. And so we have measures, we have models. The models, the projection says that the circulation is decreasing in intensity, so we go to see what observation says. So in blue are observations, and it is the measure of the water intensity, so what we call transport. So how much water goes through the system. And this is, you see that the observation, what they shows is essentially a lot of oscillations. So the climate is internal variability. So you have El Niño, you have other mode of variabilities, so the observation do not show a slowdown, but a lot of variability. While models sometimes show the correct variability, but they are not completely in phase. And the projection shows a decrease that we do not observe yet in the observation. So this is the climate projections according to the different scenarios. And you see a decrease of this circulation. But such a decrease, over 20 years of observations, we didn't see that. We just see the variability. So we don't know exactly what will happen, except that a recent study that came out 2 weeks ago said that these models that do not really resolve the the physical process of this sinking of the waters, maybe are exaggerating the amplitude. So it stays as an open question. But if it happens, this can be the consequences. So this is the surface temperature of our planet. I don't know why there is no numbers, but there's latitude, longitude, and these are precipitations. So if there is a collapse of this circulation, the northern hemisphere will be much colder, so about 10 degree colder, and the precipitation system will change slightly with subtropical precipitation moving from one latitude to the other, so impacting populations. And this is all what we know in terms of impacts if this circulation stops. So in a global warming system, there can be this kind of switch according to a global model. So instead of warming in the northern hemisphere, will be a cooling. But again, this is still an open question because models have still uncertainties. And I stop here. So the importance is always to observe the ocean together with modeling to try to understand processes, Earth interactions, and in order to respond to societal questions. So essentially forecast and more accurate projections for adaptation questions. So maybe I was a little bit too complicated for these 10 minutes, but this is it.
Thank you very much. No, I have a question, and you can ask questions. I have a question. This is complex. This may be something that's not going to happen the way it's just been projected. How to communicate about something so low chance but high impact? People read it somewhere, they've heard of it somewhere. How to communicate?
Well, in any case, whatever is the change that we will experience, we will have a lot of impacts. What kind of impacts is not clear today, but we will have impacts that will impact the ecosystem, but also us as humans. So we need just to stop rejecting carbon fossil fuels and any kind of greenhouse gases from anthropogenic origin.
So your message would be, we don't know what's coming, but just quit the fossil fuels and then we might be safer.
Yes, this is essentially the message. The quicker we stop, we will be safer.
Safer. Thank you. We're going to meet you later in the... hold on. Is there any question? There are any questions. I go to Jan Morales. Mr. Morales.
Thank you, Helga. Thanks for your presentation. If I were to do and please correct me if I'm wrong, but if I did a literature review of recent papers on the AMOC slowdown and the projections, it seems like the bulk of the newest papers are pointing to the increased likelihood that this might happen. Am I wrong about that? And if I am, what are you seeing? Yeah.
So again, this model do not simulate many processes, and in particular the convection, so in the atmosphere, but also in the ocean. So they just put a lot of fresh waters in a model that do not advect, so do not move this fresh water from glacial melting away from the North Atlantic very quickly. So it's like a kind of science fiction theme. So the latest paper that works with observation and correct and try to project what is the model state today that is wrong, and with this wrongness corrected in the future, say that the slowdown will be only 20% by the end of the century.
I have an additional question. The paper's fine. That's for scientists or who like to read, fine. But the general audience, or the journalists who have to communicate to the general audience, need a kind of easier reading piece of article which says, all right, this is what this article says, but the layering is not involved very well, more explanation to it. Are you doing that? Are you?
Well, the thing is that as scientists, we are not very numerous, and we are trying to save the observations, and I can tell you that in this moment, all this is very fragile, because ocean observations are essentially science-based.
Yes.
So it is a fight of every year, of every week, with all our organizations, and we are doing our research. We are trying to do communication. But I think what we are missing is people that are essentially dedicated to translate our scientific outcomes into a language that can be understood. So I'm teaching to political science people, but to provide these kind of elements, it takes a little bit more time and more explanation for them to understand. So if we want a more schematic view, we need to work more, but I'm not sure that we have enough time to do that.
Okay, we can help you. One question. Who of the two? You got a small one? Sorry, Maria. Well, she come back in the round table. We'll grab her in the round table then. Enrique, the Spain.
Thank you. It's a short one, maybe. What kind of ocean observations do you do to check the AMOC?
So the AMOC, we have moorings, so fixed stations that are deployed. There are today 60 moorings in the North Atlantic, and then we have at lower latitudes and in the southern hemisphere, and we measure the velocity together with temperature, salinity, etc., to qualify what kind of waters and how change the waters too. And so we know how much water is coming out from the North Atlantic and how much water is going up into the North Atlantic. So we have them. They cost a lot of money, so it's very difficult to maintain them, because the agency funding this these moorings and the ship time are always saying you are too expensive. But we are much less expensive than satellites.
That's why these conferences are for. The ocean is so important. We need the money to monitor and to know what's going on. It's about our life. Ariel, because I like you so much.
No, it's just a quick question, because besides the fact that one of the resulting causes of the slowdown of the AMOC could be some type of cooling, it would also produce dramatic sea level rises in some areas of, the globe. Like, for example, in South Florida, because it goes right next to us. So a slowdown will cause the sea levels to rise. So that's another part of the story, maybe.
Yes, but you have already a problem.
Yeah, no, it's just going to get worse.
Move from there.
We can shake hands. We're drowned already. We're getting more storms in the Netherlands. Sea level will rise much faster. And we can build dikes, but not that fast. Pretty well. Thank you very much, Sabrina. We will meet you later. Yes, thank you.